Morning, Summer. I think it's just you and me today. Since it is 9:30, I'm going to get started. I started recording and my computer is acting up still, so I'm going to hold the video off for now just to make sure it doesn't put any additional load on and we don't get booted out. As always, if you lose connection with me or if I fall out of the room, just give me 2 minutes. I'll be back in. My computer probably rebooted. If I'm gone for longer than 5 minutes, check your email, because maybe I'm having bigger issues, and then I'll just do this lecture at a later time today and then just post it. I apologize that the lecture from last week did not record. I did what I was supposed to do on my end, but the recording software in Blackboard did not take it. But that was the first week. We went through basically chapter 1 and the start of chapter 2 up through section 2.3. Today we're going to start on section 2.4 and get most of the way through chapter 2. That should keep you on pace with what is in Blackboard for what you should be following. And Summer, if you just give me a quick okay in the chat, that way I know that I'm being heard. All right, just double checking that we're all set to go. We are recording, and I have audio, and I'm going to go ahead and start. Again, if you have any questions while we're going, I will be monitoring the chat. Hello, hello. Okay. Let me close out and I'll come back in and see if there. Good morning. Can you hear me now? I've logged out and back in. Hopefully. Anybody able to hear me? Okay, sounds like we are good to go. I am recording. I'm going to now share my screen. As always, if I fall out of the room for more than 1 or 2 minutes, just give us a second. I'll be back in. If it ends up being longer, like over 5 minutes, please check your email, because chances are I had an issue that I can't overcome, and I will record this at a later time. All right, so if we're good to go, I'm going to be following the chat. So if you have any questions, jump in there or just unmute. And I do have a recording, and hopefully you can see my OneNote screen right there we'd be working from. Last week, the recording didn't go through. I did everything on my end, but Blackboard did not record it. But it was only chapter 1, which is introduction, and the beginning of chapter 2, which is force triangles. Pretty straightforward stuff. We're going to pick up here in week 2. I think this is class 3 if you're following in Blackboard, with sections 2.4, and we'll go as far as we can in chapter 2. Anything we don't finish today, we will finish up next week. So let's just jump into this. All right, last week, to add 2 forces. Last week to add two forces. We use the force triangle, which is adding the law of sines and law of cosines. We basically had a vector A, and we wanted to add it to vector B, and the result was this and this. And then we create a force triangle. That's kind of large. Let me clear that up. And we found a resultant this way, and then we used the law of sines and law of cosines to find out the angles and the magnitude of that resultant. So the idea was if you only had two forces to add together, we can use a force triangle and then mathematically use the law of sines and law of cosines. So that was last week. This week, we're going to look at, and we're going to continue with that, but the other question is if we add more than two forces, so we had more of these to do, we could use the force triangle. If we had to add those two, let's say we had to add those two plus this one, and that's our third one. There's 1, 2, and 3. We could find the first force triangle resultant and then add that resultant plus 3 and come up with, there's 3 resultant, and then we could come up with a resultant 2. So if we had more than 2 forces, we could use the force triangle more than once. And that's certainly doable. Takes a little extra work, but that would certainly work too. However, what we're going to do is look at options today. If we have more than 2, another way to solve that, and that's using vector components. And that should be review for you because you should have done this probably in algebra or trig actually, and then again in physics 1 and then in physics 2, and maybe even in calc 3 you did a little bit of this. So let's start out with here this green arrow force we have down here bottom left in our two-dimensional coordinate axes. Again, these axes can be in any orientation. We typically draw them that way, but we could have them set up. See if I can do this. We could have them set up like that. We could pick any orientation we want to have those axes as long as they are perpendicular. Okay, so as long as they're perpendicular, it's not going to be an issue. We can have those. They can be prime. If we rotate them out of the horizontal vertical, a lot of times they will make them prime, x prime, y prime, just to let you know that, hey, this isn't perfectly vertical or horizontal. But again, as long as they're perpendicular, we're good. So we have that force there. We want to find the vector components of it. So we're going to find basically the sides of the triangle or the sides of the box that ray or vector fits inside. That force will be at an angle. We'll call it theta, always measured from the positive x-axis. And that basically builds a triangle there. So we're trying to find f of x and f of y. X being the x component and the fy being the y component or projection on those axes. And that would be our scalar notation, just fx and fy. And if we were in 3 dimension, we'd have an fz. We'll get to that later. However, moving into a little easier way to establish notation for representing these vectors and their directional sense, we can get into Cartesian vector notation. Now, it's fine to stay up here in scalar notation when you're in 2D. That works really well. But Cartesian vector works really well when we get to 3 dimensions. It makes life way easier. And if you're still hesitant to sort of embrace this whole 3-dimensional Cartesian vector way of dealing with vectors, I know I was resistant. It'll make life way easier in this class when we do 3-dimensional stuff if you can sort of force yourself to learn that. Okay, so we put things in Cartesian vector form. We have in the x, y, and then if we're in 3 dimensions, we have a z direction. We're going to use the Cartesian unit vectors, which of course are I, j, and k, to designate those directions for the x, y, and z axes. So what I mean? Well, we're going to write that vector there this way. Fx in the I direction, Fy in the j direction. And if it was negative, we just put negative Fx in the I direction. If we're in 3 dimensions, we would add in there Fz in the k direction. And we typically are going to put brackets around there, and then we'll include units at the end. And what that has done is broken up that vector into Cartesian vector form, CV form, and that helps us better sort of manage three-dimensional. So real quick, let me put in some numbers here. Let's make that 10 newtons. Let's make this 30 degrees so we can write this in Cartesian vector form. I'm just going to clear out some space here. I'm going to write that in Cartesian vector form. So Cartesian vector form would have that force vector be f of x in the I plus f of y in the j. And I'll put the units in here in a second. So f of x, if you remember from trig, that's going to be 10 cosine of 30 degrees, because cosine gives us the close side with the angle, I, and f of y will be 10 sine of 30, because sine gives us the side opposite, from the angle. And that's an easy way to remember, especially when the axes get sort of spun into other orientations. So we can clean that up. 10 cosine of 30. Make sure you're in degrees and not radians in your calculator. 10 cosine of 30 should give us 8.66 I. And 10 sine of 30 should give us 5 J. And that's going to be newtons. And that will be putting that vector in Cartesian vector form. Okay. Now, we can also write it this way. 8.66. and 5, and we can put newtons there, and that's that. I've also seen it written this way. I think this is a Professor Rolone thing. And those first two, I mean, the first one and the third one are probably the preferences. This one back here and this one are the preferences, but if you write it this way, I will understand what you mean. That gives me the I and J, that gives me the components in that direction. So that should be a review. That's trig, nothing fancy there. Okay. So if we have more than two vectors, which we had talked about, so let me go to the next page here. If we have our axes, let's see if this works for me. Yeah, it's pretty cool. Liking that. And we have a bunch of different vectors on here. Let's put some in here. Let's put that 10 again at 30 degrees. Let's put 20 here, newtons, straight down. And let me give you this one, which is going to be 15. And I'm going to write it a little differently. I'm going to put a little triangle there. And we're going to find, so this is basically, I'm doing an example here, but this is basically walking through how we do Cartesian vectors. I'm going to find that resultant force and direction. Now direction is just find the angle from the plus x-axis. So that'll be x and there's y. So we're going to find the components of all these here, and then we're going to add them together. When we get to this one, I'll walk through how we deal with that. All right, so let's call this one over here. We'll call this 2 down here. We'll call that vector 3. So really what we're trying to find is a resultant vector is going to be the sum of all those individual vectors, which means we're going to have F1 plus F2 plus F3. Now, again, you could do a force triangle with 2 of them, then use that resultant to go to the force triangle, build a force triangle with the third one. Just takes a little more work, I think. All right, let's go through all these. Now, you may have done this enough that you can sort of do this in all in one shot. I'm going to go through and sort of do the basics, and then you can sort of condense as you need. All right, so this first one is 10 newtons at 30 degrees. We're going to write that in Cartesian vector form. So their F1 is going to be, as we saw earlier, 10 cosine of 30i plus 10 sine of 30j, and that ends up being 8.66 and 5.0 newtons. And we did that on the previous screen. Excuse me. All right, F2. F2 is basically 20 newtons at, that would be at 270 degrees. Right, 270 degrees. We're going to keep it from the positive x-axis. If I want to write that in Cartesian vector form, there's 0 in the I direction minus 20 in the j direction. So I'll just put it in that notation there, 0 minus 20 newtons. And there's that second one. Again, put in I and j in the x and y components. All right, let's deal with the third one. This one's a little different. Now, there are people, and you may be one of them, and I am one of them, have been one of them, where I want to find out, just because I'm so used to doing it this way, I want to find out what this angle is. Because once I know the angle, then I can use sine and cosine to solve it. But we're given this little triangle here, which is kind of unique. Okay? This triangle here is a 3, 4, 5. And you could check that with Pythagorean theorem. It works out. If you remember, cosine is co from the SOHCAHTOA, sorry. And that means its ratio is going to be, cosine is the adjacent, so that would be the 3 over the hypotenuse. And then sine would be so, which is the side opposite over the hypotenuse. So that means where we would write, for the 3 one, we'd say we'd say 15 cosine of that angle I plus 15 sine of that angle j. We can substitute that cosine and sine with these ratios. So I really just write 15. Instead of cosine, I put 3 over 5. And then for sine, instead of writing sine, I put in 4 over 5. And that becomes my j. Now we have to be careful because we're using that triangle. We're taking all the angles as positive. So technically this one is going to be negative here because we're in that second quadrant. So becoming negative x. But that is, using this is way easier when you see it presented that way than going through and calculating the angle. I could go through and use tangent and find that angle, but then I'd have to still cosine and sine it. This actually makes it, I think, a little easier. So if we go through the minus 15 times 3 over 5, this 3 was at minus 9, 12. I'll see if anybody yells at me to say that's incorrect. All right, so if we add those all together, if we want to find the resultant, what we have to do, running out of space here, what we have to do is sum the x's and sum the y's, and then put them back together in a Cartesian vector form, and we have the resultant vector there, and then we can find the magnitude from that. All right, so let me jump to another page here. I'm going to have to jump back and forth to get these values. So if we're going to sum all the x's, in the x direction we have an 8.66, a 0, and a minus 9. So 8.66 plus 0 minus 9 equals minus 0.44. In the I direction. We sum the y's. I'm doing there, 866, 0, minus 9, okay. We have 5 minus 20 and 12. 5 minus 20 plus 12. What's that give us? This gives us minus 3 in the J. So to write our resultant vector in Cartesian vector form, it would be minus 0.44 minus 3 newtons. So if you're asked for the following problem, write the vector in Cartesian vector form, the resultant vector, that would be it. Okay. Now, again, you could write it as minus 0.44i minus 3j and put brackets and newtons. That is fine too. Same thing. All right, I'll take a moment. Questions, what we did so far before we finish this problem. Okay, quiet in the chat, so I'll keep going. So how do we find the magnitude? Because we were asked to find the magnitude, which is FR. FR with the arrow on top is the vector form of it. We want the magnitude. How long is that vector? Well, if we just try to draw it out here, it's going to be minus a little bit and minus a little bit. Okay, does that make sense? Let's look back at our problem here. Yeah, we're pulling down 20 here and 15, so I suspect our answer will sort of be over in this area, which it is, because we're pulling 15 and 20. So that way against the 10, it's going to skew everything to the third quadrant. So that puts it somewhere down around here. Our resultant vector is down this way. Now that's the angle we'll eventually want to find, but since we build it that way, we are building basically the x and the y components. So to find that magnitude, we're just finding the hypotenuse. And using Pythagorean's theorem, we can find the hypotenuse because the hypotenuse is FR, and FX is our A, and FY is our B. We can find that from squaring the x and squaring the y components and then taking the square root of that. Let's see if I can do that quick. I should have picked easier numbers. 0.44 plus 9. I'm getting 3.03. Now that's just the magnitude. That's the amount. That's how long this vector would be if we drew everything to scale. And that makes sense because that triangle, if that's minus 3 and that's 0.44, this side has to be greater than 3 at a minimum. All right? Less than the sum, but greater than either side. All right, how do we find the direction? Let's finish this problem. The direction is really find theta, and we want to have it from the plus x. That's very important. And we're going to find that basically by doing inverse tangent. So again, looking at this triangle, we're going to find this angle, and then we're going to add it into that angle to find, or use that angle to find what it would be from the plus x. So inverse tangent is always the y over the x, so that's minus 3 over the minus 0.44. And let's see, 3 divided by 0.4, inverse tangent, I'm getting 82 degrees, right? 82 degrees actually ends up being that. And we add 180 to that, and we'll get 262 as the thing. So our answer is 3.03 newtons at 262 degrees. And that would be our answer for the problem. Our answer to the problem there. And they say why, well, why am I getting 82 instead of this smaller angle when I was looking for this one? Since I put this is the y and this is the x, I was putting this over this side, which is really the tangent of that angle. That's why that's 82 is there instead of finding this angle, which I originally was going to look at. If I wanted to find that angle, I had to put 0.44 over 3. Since I did this ratio, it gave me this angle. I add the 180 to it. I get my final answer. All right, so that's using vector notation. Questions on that problem? That's a nice exam problem. If I was taking notes, I'd probably put an asterisk there to make sure I studied that problem. Hint, hint, and hint. Okay, it's still quiet in the chat. I'll take that as everybody's good or has fallen asleep. Either way is good. Again, I have more practice problems in my lecture notes that are online. So I'm not going to redo those problems for you. You can follow those. What I always tell my statics class, the only way to learn how to solve these problems is to solve these problems. So like if you want to run fast, guess what? You have to start running. You have to run fast. So do a lot of problems. What I recommend you do is when you get to the problems in the book or you get to the problems in my lecture notes or you get to the problems that I do on my YouTube videos is to cover up the solution. And don't look at the solution and say, yeah, that's what I do, because all you're doing is confirming what I did. That's not you learning how to do it. You have to force yourself to learn how to approach it. Don't worry so much about the math to finish it. Worry about the approach so you have a good starting point. Okay? So there's other problems there, and I'm going to keep moving forward on to a little more Cartesian vectors, and this is going to be dealing when we get into 3D. All right, 3D. All right, so Cartesian vectors. When working in 3 dimensions, using Cartesian vectors or the Cartesian vector form, that's I, J's, and K's, makes life way, way easier. Okay, way, way easier. Now, when we go into 3 dimensions, hopefully you've already covered that or started to cover that in your Calc 3 class, or maybe you've used it already in your physics class. I'm going to give a quick review here. We're going to always stay with the right-hand coordinate system. The right-hand coordinate system means we're going to build it with our right hand. Okay? You remember right-hand rules probably from Physics 1 and from Physics 2. We use our right hand for the coordinate system. What that means is if I have 3 axes, so they're all mutually perpendicular, and I make this the x, basically x will curl into y to go into z. So x goes to my y, gives me the z, and usually the z is in the thumb direction. Okay? If you think of this right here as the corner of a room, so that would be that back corner right there. This would be the xz plane. This would be the yz and z plane, and down here would be the xy plane. So no matter which way we go, so if I take this and make it this way and I make this x, x will go into y, right? Basically curl x into y, and my thumb points and gives me the z that way. So that's where our orientation will be. And that's typically how we'll look at 3 dimensions. We can set it up different ways. We could set up x and y like this, like we do in 2D. And where's the 3rd dimension? Well, x goes into y, thumb points out to z, which comes out of the board. So that's more for 2D. This one we looked at for 3D. Okay? In 3 dimensions. So what that means is when we have a vector here, what does it mean when we go into, and we have a vector sitting out here in space, there's our 3D vector. If we take that projection, it'll take us down and find the XY plane. It'll have a projection right along the XY plane. And instead of filling a box or a rectangle, this actually fills the volume, which is truly a box, that vector sits inside. So this vector in 2D goes from one corner to the other. In 3D, it goes from one corner of the box to the other corner of the box. And that gives us a 3D vector, which means when we write that in 3D, we're going to have an f of x in the I, f of y in the j, and f of z in the k. And then I'll have units too. Okay. Now, again, the I, j, and k is a little vector, unit vector that points in the direction of those axes. So the x, y, and z are really the I, j, k axes, if you want to think of it that way. Okay. Now, let's say we've gone through, we had a bunch of 3D vectors in here, and we did the same process we did last time, and we found them all in their x, y, and z's, and then we summed them all together, and we got a resultant vector right here. Right? Let's say this is our resultant vector. After adding up 3 vectors, we add the I, j, and k together, and we get that final vector. This is the vector, again, in Cartesian vector form, C, V, F. What if we want to know the magnitude? Well, we do the same thing. It's almost like Pythagorean's theorem in 3 dimensions. We would take the magnitude is the square root of the x squared, the y squared, and the z squared. And that gives us the magnitude. That's the length, the physical length of that vector, mathematical length of that vector in 3 dimensions. Okay. Now, what about finding the direction? We found the magnitude. Let's find the direction. Let me leave some space here because I want to stay on this page. Let's see. Oh, technology is pretty cool. All right, let's find the direction over here. Oop. Let's find the direction. Try it again. Find it over here. Okay. When we get into 3 dimensions, up here, well, let me take it back. In 2 dimensions, theta is the direction, right? When we get into 3 dimensions, we actually have 3 angles that we're going to look at. 3 angles. One is going to be measured from the x-axis, one will be measured from the y-axis, and one's measured down from the z-axis. All right, an x, y, and a z. Okay, sorry about that. There's reboot number 1 for the computer. All right, up to this point, everybody okay? What we covered so far, any questions, anything? I'll check the chat here.
Hey, you cut out right as you began the direction part.
You mean all this blue stuff down here?
Yeah, like right before you got to that. If you
So
could
where
just
was I? I was
walk over
here.
it.
Did I do the magnitude already?
Yeah, you
The pink
just,
up in the upper corner?
yeah.
All
But then
right.
you wrote green, and then that was it.
All right. Let me go through this blue part down here.
Thank you.
No worries. Thanks for alerting me to that. All right. That was fun. Love Windows 10. All right, so where were we? We're looking at here. We talked about getting the magnitude, right? We built this vector here in. We built this vector. We talked about having 3 vectors. We summed them together, and we came up with this resultant here, and we could find the magnitude. This again, Cartesian vector form down here. We could find the magnitude the same way we did in 2D by using like a 3-dimensional Pythagorean's theorem. So I think that's where it cut off. So how do we find the direction? Well, that takes us over here. And in 2 dimensions, I'll get a better color here. In 2 dimensions, when I have that vector, right, we called that theta, and that was the angle off of the x-axis. We could call this another one. We could call that phi, which is the angle measured from the y. But once we have the theta, we don't need that. We know that this one is going to be 90 minus theta. So we don't need to have a second angle there. That's in 2D. When we get to 3 dimensions, however, and this is 3D down here, we need more than one angle to get the orientation of that vector. We can't use theta because theta is in the xy plane, right? So we're going to use, from the x-axis, we measure it as alpha. That's going to be this right here. Okay, alpha is going to go from the x-axis to the vector. In the y direction, we're going to go from the y-axis to the vector. Again, axis to vector using beta. And then from the z-axis, we'll measure down. From the z-axis to the vector, we use gamma. Now, those are special angles in 3 dimensions. They go from the axes to the vector. From the axes to the vector. Those are called direction cosines. And that's what I have written right here. Direction cosines. We could also call them direction cosine angles or direction angles. But there are direction cosines. They tell us where the vector is oriented in 3-dimensional space from the x, y, and z axes. All right, so why do we call them direction cosines? Well, direction cosines is because that's how we can calculate it. If you remember from SOHCAHTOA, there's the ca part. That's going to be adjacent over hypotenuse. So if I say cosine of the alpha, it'll be the adjacent angle, which is f of x, over the resultant. Again, how much of the component is along the x direction? That's the adjacent over the vector. It's really hard to draw in 3-dimensional space, but if I have that vector up there, I'm not going to be able to do it. It's kind of trying to build this side with this side and that vector in there. And that's really impossible to even say. But yeah, it's drawing 3-dimensional stuff on a 2-dimensional space with a 1-dimensional tool. So anyway, let's come back. Cosine alpha would be the x component over the resultant. Cosine beta, which is the y, is the component in the y direction over the resultant. Cosine gamma is the z component over the resultant. Okay? Again, always measure from the axes. So alpha will tell us the angle from the x-axis, beta from the y, and gamma from the z. Okay.
So does it just flatten the vector, or is it like measuring the angle between it?
It's going to measure the angle between. Let's see if I can. Give me a sec. I'd love to see if I can pull up a. See if I can do this without my computer dying on me. I'm going to see if I can bring up in an image. That's not too bad. Let me see if I can get that one in here. Pull up a new page. Nope. There. Wow, that's kind of cool. All right, so there's our vector. I wouldn't call it U, but that's what they choose to do. Let's just call it, we'll call that A right now. You know, F implies that it's a force. Let's just say any vector. Down here are alpha. Alpha, again, is measured from the X to the vector. Beta is from the Y to the vector, and gamma is from the Z to the vector. Those would be our direction cosines. And what we're trying to build, that's that angle right in here. So if I was able to draw a line from here to here, this technically would be a right angle right down here. So if I can pull that triangle out, I kind of have this. There's A. Okay. And over here is my A in the X direction. So to find that angle, which is alpha, right here, we're really taking this side, A of X over A, to find that, which is cosine. Not sure if that helps visually. See if I can pull another image in here that would be helpful. Did that clear it up there for you at all?
Yeah, I'm just kind of I'm trying to see like what it's locked to is the wrong word. Like what it's when you drew that right angle, that really helped. Like from the alpha at the bottom there.
We're basically trying to take that three-dimensional and put it into a two-dimensional. Because once it's in a two-dimensional, then we can sort of use that kind of stuff.
Sure. Okay.
But without being able to rotate that, even though this is a right angle, even though it doesn't look like it. This one looks like a right angle.
Yeah.
But it's not. But it starts here and it comes out here.
Okay.
When I take A and project it down, it actually comes to here.
So it's like the shadow of it.
Yeah, you can think of it that way. And this angle is 90 degrees also. I'm looking for another image here that would. They don't really have anything that's.
I get like a 3D graphing tool or something.
Yeah, there's a number of things. I didn't even do a new snowblower. I got halfway through. It broke at the bottom of the hill where I live. Yeah, of course. That's how I roll, man. That's how I roll. All right, let me see if this image will help. This one's any better. All right, the red angle there, the red vector, goes from that corner of the box down here to this corner. Its projection is really down here into the XY plane. And what it's trying to do is when we do the inverse cosine, it's actually trying to work with this triangle here. That has the, I'll call it A of X along this base, and this is actually the A resultant on that side. Not sure if that helps or not.
Yeah, thanks.
Okay, no worries. All right, let me continue with that. And I think once we get into some problems, it's going to clear things up a little bit more. All right, one other thing I need to introduce here, you've probably seen if you've had in Calc 3, is a unit vector. Try that again. It's a little U. A unit vector is unitless, and it's 1 unit long. So it doesn't have any units, and if you multiply something by it, it doesn't really affect it. The unit vector is just sort of sitting down here in the corner and it points in the direction of the vector. All right, sort of like the tattletale, it says it went that way. And a unit vector, the unit vector is equal to, we have the unit vector of A, it's going to equal the vector A over its magnitude. Okay, now that's a general case for the entire vector. If I take just AX over A, we saw that earlier as, well, that's cosine of alpha, not the entire vector over A, but just the component. That would give us the unit vector just for the X axes. Okay, and we're going to use this relationship. I'm just introducing, we'll use it because the vector is going to be the magnitude times the unit vector of that vector. And we're going to use that a lot coming up here. So let me just get ourselves to almost to a problem here and give you one or two other identities. I said earlier on this two-dimensional space up here, over here, if I know theta, I can figure out what phi is because it's 90 minus. When we get into 3 dimensions and we're using alpha, beta, gamma, the relationship we have between is cosine of alpha, cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma equals 1. Meaning if I know 2 of them, I can find the third angle. Which goes to say, at times, if you're given a problem, they'll give you alpha, they'll give you beta, but they may not give you gamma because you can find gamma if you need it. All right, so that's a nice one to have in case we ever need it. All right, before we get to a problem, addition and subtraction in 3 dimensions. Addition and subtraction. If we're trying to find the resultant force, again, we're just going to add up all the x's and make the I, add up all the y's, that'll be our j, and add up all the z's, and that'll be our k. And subtraction is just adding a negative. Okay, so we're going to add up the x's, make it I, j, and k. Same as we did in 2D. I'm not going to spend much time on that one. Okay, let's go through and do a problem here. Let's see if it lets me do this with the axes. Nope. Yeah, not really loving that, but I think I can do better if I just draw it myself. All right, let's go through and do an example problem here. There's a couple different ways we're going to see vectors drawn. As I said in 2 dimensions earlier, we can be given the angle. It could be along an axis, or sometimes they give you that little triangle. That's about the extent of what you'd see in 2D. Once we get to 3D, however, and we'll have x come out, y, and z is typically the vertical for our 3-dimensional problems. A couple different ways they can show us vectors. And let me draw a few of those, and then we'll go from there. All right, we can have one that's directly along the axes, and you would see it drawn like that. We could also have one along the axes, and it's given that little triangle, right? 4, 3, 5. So I'll call that vector 2. There's vector 1. And again, when it's drawn that way, it is along that plane. Okay. At times, they will draw it like this to show you that it's, and put it in a box to show you that it's inside that plane, but not always. I'm going to see if I can bring up a better image that shows some of these different ways. Just give me a moment. I'm not seeing anything too hot here. All right, I'll just continue with drawing it. That seems the best way to go here. Other ways we can be given these vectors. If a vector sits below the plane, right? So if we call this like the corner of the room, if the vector starts in the corner of the room and points down into the basement, they will draw it like this. Okay, this will be a little darker, so we know that's the vector, but it'll show this sort of square here, which is in the XY plane, and this goes below sort of a negative Z. When they have it drawn that way, they will typically give you this line. They'll put a right angle there, and they will tell you what that angle is right here. Sometimes they'll be even nice enough to give you that angle, but they'll also shade this to show that it's a vertical plane and not some other plane.
That angle is gamma, right?
No, gamma is always measured from the z-axis, so this would be gamma here.
Okay, thank you.
Okay, that would be gamma, over here would be alpha, and there would be. And that's the third way or fourth way. If I have some vector up here, they could just tell you alpha, beta, and gamma, and then you're done. So a couple different ways there. Using that little triangle, just measuring it from an axis, showing that it's above or below, and then also using direction cosines. All right, couple different ways just to recognize how we can be given problems. All right, let me see if I can grab this right here. It's gonna let me do it. Come on. I'm trying to grab a problem so you don't have to live through my. Let's see if it did it. It worked it? Nope, didn't work. Hang on. I'm trying to make this grab a problem so you don't have to live with my drawing. That might work. Let me see if that one works. There we go. A little better. I mean, it's a picture of my drawing, so I don't know if that's better for you guys or not, but I think it's drawn fairly cleanly there. Okay, so in this one we have just two angles. All right, our two vectors, sorry. We have F1 down here. F1 is 180. It's shown as acting below the surface. If you can see that, it sits below the XY plane, this negative Z distance. And then we have one over here that's set up with direction cosines. Okay, direction cosines. And let's put some numbers. Let's see, can I put some numbers in here? Yeah, let's make this 30 degrees. We'll make beta 120, and I can't just guess what gamma is going to be. I'm going to have to find out what that is. So cosine squared of 30 plus cosine squared of 120 plus cosine squared of gamma equals 1. Let's see if we can figure out what gamma is from that. 30 cosine squared plus 120 cosine. And let's just make this 30 also. I don't think that's exactly it, but just for the sake of time here and holding you all up. All right, so we want to find the resultant force. The resultant force is going to be adding up all the forces, which means it's going to be a combination of F1 plus vector F2. And again, setup is the important thing. Math is certainly important to finish it, but we got to set up the problem first. So let's go ahead and find these. Basically going to build each of these into Cartesian vector form. Let's start with F1, which is the 180. Now, 180 sits below the XY plane. That's shown by this box right here. It sits down below. So we have to do what's known as bring it up and over. Up and over means up into the XY plane, and then over to the X-axis or the Y-axis. Okay? We have to bring this up because this sits right now below that plane. So we're going to bring it up using trig and then bring it over or back for the X or Y. So in the X direction, so if I write F of 180, in the X direction, it's going to be 180. I bring it up. That's going to be cosine of 15 degrees. That brings it up to this line right here. And since I know this is 60, that makes this 30 right here, because that one's 60. I have to cosine 30. That's to bring it over. This brings it up, and that brings it over, and that'll be our I component. Let me do the Y, and then I'll ask for questions. Y will be 180. Cosine 50, that brings it up. Now we have to push it back to the Y-axis, so we're going to use cosine of 60, and that pushes it back to give us the Y component. So this is the X component of 180, and this is the Y component of 180. And lastly, in Z, it's going to be 180. Now, I don't have to bring it up or over. I just have to find this side right here to give me the Z. It is in a negative direction, so I have to make it negative 180 sine of 15 degrees. And that gives me the Z component. All right, before I go any further, because you'll see this set up a lot, questions on what I did there. Bring it up, cosine it over, cosine it back, or just find the Z. I know it's a strange way to present it, but
That's just putting it like back in the normal coordinate system, I guess.
when you bring it up, you're putting it in the XY plane, and then you can use trig, sine and cosine.
Okay, cool.
We're trying to take 3D, bring it to 2D, and then find the component, which is 1D.
Okay.
And that's each I, J, and K. So if I go through that math-wise, that comes out to be, I think, 151-ish, 87, and you can check the numbers later, but this is just a negative 47. And we are in newtons. So that would be that vector in Cartesian vector form. All right, let's build the F2. Now, we know these are direction cosines, one because it says alpha, beta, and gamma. But if it didn't, we have to have the angle go from the axis straight to the vector. This 15, this 30, this 60 here don't go straight to the vector. They go to a component of the vector. The 30 here, the gamma here, the beta here, they all go from axes to vector. That means they're direction cosines. That means if we make F2, let's just make F2 equal to 100. That becomes 100 cosine of gamma, or alpha, which is 30, plus 100 cosine of gamma, which is 120. That's our J. And 100 cosine of gamma, which is 30, and that's our K. And if we go through that, I think that's 86.6. 120 is going to be, what's that, 50? Cosine of 120. I'm trying to visualize it. Yeah, minus 0.5, I'm pretty sure. And 100 cosine of 30 again will be 86.6. Yep. Brackets, newtons. That would be putting that into Cartesian vector form. All right, so what are we going to do more with this problem? Let's clean this problem, leave some space here. I'm going to clean it up a little more. Give some space here. If we want to find the result, we're just going to add the x's together. So that becomes 151 plus 86.6. Gives us about 237 something, 6. The minus 50 and the 87, so that becomes a plus 37, and then the minus 47. That should give us 39.6. That becomes our resultant vector in Cartesian vector form. Now, looking at the way those two forces are pulling, does it make sense? Well, without having these drawn to scale with these angles, I guess it could make sense, but we'll get to that a little later. All right, how do we find the magnitude? Just the magnitude is going to be the square root of the squares of all those. So 237 squared, 37 squared, 39.6 squared. And I don't have that value in front of me, but the math doesn't matter so much, just the process. And then find the direction. In 3 dimensions, again, we're finding the direction cosines or direction angles. So alpha is going to be inverse cosine of the x, 237 over the resultant, right? I'm just going to put a box there. And we'd find out how many degrees that is. Same thing for beta. Beta will be the inverse cosine of the y component, that's 37 over what our resultant is, then we can find that angle. And then gamma would be the inverse cosine of the y component, 39 points, or z component, sorry, over the magnitude, and we can find that angle. Now, again, I didn't finish out the math just because I don't want to waste more time on the calculator. I'm trying to make up problems so you have additional problems in the lecture notes to go through. But that would be a really good practice problem for vectors, adding vectors in 3 dimensions. All right, any questions there? We have a little bit more to finish up on a thing called position vectors, which you probably have seen in physics and most likely in Calc 3. But before I move on to that, any questions on that? I like the names it gives the pages over here if I don't patios. All right, let's move into a thing called position vector. A position vector is exactly what it sounds like. It's a vector that gives the position of a point in space. And they use r, lowercase r, as the position vector, sort of for radius. Now, if we're in 2D, and we had this point here, we'll call it x and y. We'll call that point A. We'd have a vector goes from the origin to that. And we go over x, we go over y, and we get to that coordinate. The position vector for that would be, so for point A, would be I go X in the I direction, and I go Y in the J direction. And it has some units, let's call it meters. That locates that point with relation to that, to the relation to the origin. Okay, so it locates a point in space in our reference frame. You would walk X and then walk Y, walk X, walk Y, and you get to that point. Same idea in 3D. If we're trying to locate a point in space, and let's say it sits above that XY plane, if that's our position vector, let's call it point B. Point B will have an XY and a Z coordinate. An XY and a Z coordinate. I walk X, I walk Y, and I walk Z, I will get to that point. There's X, Y, and Z. And obviously, if they're negatives, we'd walk in the opposite direction. So the position vector locates that point with respect to our starting point. And here's the origin. All right, so there's the XY plane box here, and there's it goes up Z. And again, we could have direction cosines. We'd measure them this way, right? Alpha, beta, gamma, just so we're seeing the same thing. So our position vector here, if we wrote it, would be position vector of B, would be X plus Y plus Z. And we have units. That would be our position vector, or the vector that locates the position of that. Now that's if we start at the origin. What if we don't start at the origin? What if we have 2 points in space and I go from point C over to point D? Okay. I want to go from point C. So I want to find the position vector that goes from C to D. All of these we started at the origin, so we just walked X, Y, and Z. For this one, we have to walk, obviously, how far in the X, how far in the Y, and then how far in the Z, as if we put our coordinate axes right up there. But since our axes are down here and not at point C, they're at the origin, not C, how do we deal with that? Well, C is going to have an X, Y, and Z coordinate, and D will have its X, Y, and Z coordinate. And we could put little D's in there and little C's in there to designate that. What we did for this one is we basically had the coordinate and the origin. So the difference of those two was X minus 0 was still just X, Y minus 0 is still Y, Z minus 0 is still Z. Here we're going to have to take the difference. So to write this, we're going to take the X coordinate of D, that's where we're going to, minus the X coordinate of C, and that'll be our I direction. Then we take the YD minus YC, that's our J, and our ZD minus ZC, and that's our K. And then we have units. So that gives us a position vector in 3D if we do not have it starting at the origin. Okay. Now, where does that sort of idea come from? Well, just to give you a little bit of the background. Okay. If we had that position vector from C to D, right, and we'd write that C to D means C to D. That's from 2. And we had those 2 vectors out there, right? Well, let me use this one still here. There's our position vector RC, and there's our position vector RD, okay, from the origin to those points. So what I have in here is RC, RD, and from there to there is RCD. If to write that out in sort of equation form, I have RC plus RCD equals RD based on that drawing. If I just want to find RCD, I would subtract RD minus RC. And that's basically what we did right here. All right, so there's some background for you on how we get to that. And that gives us a position vector directed from C to D. Okay. So the last thing I have for us today is to do a problem on that. That ends our lecture here for week number 2. So let me just make up a problem. And we'll call it position vector problem. And I'm just going to make up one here. See if it'll let me do this. All right. Not bad. We still have to come out of here. Nope. Nope. You know, it'd be a lot easier just to draw these. There we go. All right, we're going to be given 2 points. Point A is going to be, oh, I don't know, 3, 5, and 6. Point B will be 6, 10, minus 6. And if we plot those 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, A would be somewhere around there. 5, 6, 10, that comes out here, minus 6. B's down here. And we want to find position vector from A to B. We can find alpha, beta, gamma of that position vector. And we can find the distance between those points is really just finding the length. So just playing with vectors a little bit. All right, so we want to know position vector to go from A to B. So I'm going from A all the way down to B. That's going to be position vector AB. All right, how do we solve this? Well, we're given the points. So let's see if we can build that position vector right off the bat. Position vector A to B is going to be the difference of the x's. Again, we start with the x of the second one, the 2. So that's going to be a 6 minus 3 in the I, plus a 10 minus 5 in the j, plus a minus 6 in the k. And if I go through that, I end up with 3, 5, and minus 12 meters. That's our position vector. It goes from A to B. Locate the position of B in relation to A. Now, how do we check that? Well, the idea is we're going to walk 3 in the x. So we'd have to go 1, 2, 3, right? We're going this direction, 1, 2, 3 in the x. 5 in the y, 1, 2, 3, 4, 5. 5 in the y. And then minus 12 in the z. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So plus 3, plus 5, minus 12 should get us to that point. Ballpark it does, so we're confident that is okay. All right, so that's position vector. Let's find the length next. The length of AB is really just the length of the vector, meaning the magnitude of that vector. We just have to find the length of this. That's the magnitude of it. How do we get the magnitude? That's equal to the square root of the squares. So 3 squared plus 5 squared plus a minus 12 squared. So at 9, let's see, 144 plus 25 plus 9 equals square root 13.3. That tells us the length or distance between those 2 points. It could be helpful to know, right? All right, last one, direction cosines. Alpha is inverse cosine of the x component over the length, 3 over 13.3. Don't forget to take inverse cosine. Beta, inverse cosine of the y, which is 5 over the magnitude. And gamma will be inverse cosine of the 13.3. Now, careful when you do this last one because it has a negative right here. Careful when we do the last one because of the negative. If we look at this vector, and if I put the axes right up here again, right? There's my axes. If I sort of slide this up there, that direction cosine, there's the alpha, here's gamma. So beta. Gamma's coming all the way down here, which means it's going to be greater than 90 degrees. So careful when you get this one. Because of the negative sign, it's possible it's going to give you an angle less than 90. But we need something greater than 90 because it passes the 90 degrees here and goes further down. It's below the XY plane, if you want to think of it. If here's the XY plane, this sits below that, so it's got to be greater than 90 degrees. Just be careful when you do that last one. Okay. All right, questions on that? I want to throw one last thing into this problem, sort of try to bring it full circle and reintroduce this idea of the unit vector. The unit vector, again, is the component over the magnitude. Okay? The component of the magnitude. So we could use the unit vector could be the component. I'm sorry, I have those backwards. The vector should be the vector over the magnitude. I'll just put a big V. We could put R from A to B over its magnitude. And we can build the unit vector. Okay. If we rearrange this, I'll put over here, rearrange this, that vector from A to B is equal to the magnitude of that vector times the unit vector. And that unit vector points in a direction. So that's sort of the I, J, and K components that go along with that. We could put cosine all there. So we're going to start seeing this relationship and how we use the unit vector to tie all this together there. All right, questions on that problem? Okay, so where do we go from here? We're really spending time, once we know how to deal with 2 and 3 dimensional vectors, we now need to move into how they will be presented. We've already talked about the different angles and the different ways it'll be shown. You know, we had where we're given a little triangle, the 3, 4, 5, where it's told us it's below, and they sort of show us this surface, and they show it how far below it is. We've been given it to with the direction cosines. The next way we deal with cables is if we have maybe a point here and the cable pulls through that point. So it's a force directed along the line through a point. How do we deal with that force? How do we deal with that force? And where we're going to go is finding that force vector is going to be taking the magnitude, as I said a few minutes ago, times the unit vector, which is the only time when I ask you how do you create a unit vector for force, using a unit vector to create a force, you would say FU, and I would say thank you, you're correct. But that really comes out to be the magnitude times the position vectors. And we're going to use this relationship to really start to build forces into Cartesian vector form. Okay, so that's where we go next. And that sort of brings it full circle with how we handle forces in 3 dimensions. And that's really the first exam is all about that, building forces, adding together, finding the resultant, finding the direction cosines. After that, we start dealing with forces and how they can create rotation or potential rotation with a thing called moment. In physics, we call that torque. Same thing. So that would finish up lecture today. For those that are still with me, any questions on what we covered there? And if you're all good, you're free to go, but I'll hang on here for a moment to see if anybody speaks up. If not, have a great day. I hope your snow has stopped and you're able to shovel out.
Thank you. Have a nice day.
No worries. You too. Thanks.
Bye-bye.
Jen, you okay? All right. You have a good day too. Thanks for hanging in.